Hi folks, welcome back to Math with Captain Rod. Making this video here to go through an example of how exponential decay or growth works here. So this is number 34 in session 6.7 in the Openstax College Algebra text. So it says, let's see, a scientist begins with 250 grams of a radioactive substance. After 250 minutes, the sample has decayed to 32 grams. Rounding to 5 sig figs, write an exponential equation representing this situation to the nearest minute. What is the half-life of this substance? So, right, exponential growth comes from I like to start by talking about compound growth, such like compound interest problems. So for compound interest, you have, the amount of, let's say, money invested is equal to your principal times 1 plus r over n to the nt. This is used for cases where you're compounding like twice a year, 6 times a year, 100 times a year. Now, as the n gets really, really large, basically what happens is this amount is equal to your principal times e to the rt, if n goes to infinity mathematically. So this is used for, oops, and I forgot the rt, forgot the r in the rt. So these equations basically do the same thing. It's just that this one is used for finite numbers of compounds, like if n is, your money is compounded twice a year, or 12 times a year, or maybe 360 times a year. This is used for continuous compounding. So this is used for like population growth, or in this case, this radioactive decay. Because what you have to realize here is that, every second that goes by, some of this stuff is disappearing. So we're going to start with this. All right, so the amount that we have is going to equal, all right, this P, now in the terms of money, usually stands for principal. But whatever it is, it's your original amount. In this case, it would be the original amount invested. Here, it would be 250 grams. I'm going to leave out the units and just take a note that that's in grams, right? Times e to some constant times t, or I'll put r times t. Doesn't really matter what you call this r. Sometimes you'll see it c times t, sometimes k times t. Here I'm just going to put r times t. So here's our model here that will tell us the amount of this stuff against time. What we don't know yet is this rate constant here. Now, what we do know is that after 250 minutes, we have 32 grams. So in this example, that means if t is 250, our a is 32. So I'm going to go ahead and put that in there. 32 equals 250 e to the r times 250 minutes. Whoops. A little weird. 250. All right. Well, they're both 250. That's okay. I would not have made those the same if I made up this example. This is just kind of coincidence. We're starting with 250 grams, and then after 250 minutes, these generally will be different numbers. What we can do now is solve this for r. So I'm going to go ahead and divide both sides by 250. I'm going to do this in decimal form. So 32 over 250 is 0.128 equals e to the, if you don't mind, I'll write that 250r. Now we want to solve this for r. To get it out of the denominator, or out of the power, what we're going to want to do is take the natural log of both sides. So ln of 0.128 is going to equal, and I'm going to skip this step and just write it 250r times natural log of e, which is 1. So r is going to equal natural log of 0.128 divided by 250. And I got negative 0.008. It says 5 sig figs. I'll go ahead and honor that. 2229 is what I got out of that. There's our 5 sig figs. Honestly, I think that 2 sig figs is just fine. And I'm going to go ahead and rewrite it now. Right? A equals 250 e to the r, which we just found, minus 0.008229t. So there's our formula here now that will model this 250 grams of radioactive material decaying off. It says to the nearest minute, what is the half-life of this substance? So the half-life is the time for the amount of material to be cut in half. If we started with 250, half of that would be 125. So what we'll do is we'll put 125 in for the amount. Oh boy, 0.08229t. And we'll just need to solve this for t. 125 divided by 250 is 0.5. This is solved by taking the natural log of both sides. So we're going to have natural log of 0.5 on the left. And again, I'm going to skip a little step here. If you take the natural log of this and then use that beautiful property that this can come out in front, this is going to be minus 0.008229t times natural log of e, which is 1. So t is going to equal the natural log of this number divided by this thing. So go ahead and see what we get here. Natural log of 0.5 divided by minus 0.008229. We get 84 for t. Now it says, I think, to the nearest minute, right? Yeah, to the nearest minute. It's 84.23. There's your nearest minute. At about 84 minutes, this material, the amount of the material will be cut in half. We'll be down to 125 grams. So I hope that this video helps demonstrate how to apply an exponential growth type of model. Again, it's very similar to compound interest. It's just continuously compounding. For continuously compounding things, we start with this. That's what this thing's used for. Typically, it's population growth or decay models like this. Things that are constantly changing, like the population of the Earth. As a second goes, even 1 second goes by, the Earth has changed in population by some amount, or rabbit populations, or I always talk about the snakes in Florida. Somebody somewhere in the Everglades let a couple pythons go, or maybe multiple people did, and that thing, population of pythons against time looks something like that, and could have been modeled reasonably well using this type of mathematical model. So I hope that this helps demonstrate how to use how to apply exponential growth models, and have a great day.